Okay, go ahead. Yeah, you can start. Yeah.
Hello, everybody, and welcome back from lunch. We are now ready to start with the afternoon session of this workshop. And so this session is about by statistical matching, imputation, and modeling. And we are going to have one speaker, of course.
I'm going to steal this. Okay, I'm sorry, everybody.
No, not a problem. Actually, we look good. We do have slides up for our first speaker, who is Jerry Reiter. And he is going to be, as you can see, presenting by WebEx. He is a professor of statistical science at Duke University. He has a PhD in statistics from Harvard University and his bachelor's in math from Duke. He participates in both applied and methodological research in statistical science. His methodological research focuses mainly on statistical methods for protecting data confidentiality, for handling missing data, and for modeling complex data, including methods for causal inference. He is the principal investigator of the Triangle Census Research Network, which is funded by the National Science Foundation, and this is to improve the practice of data dissemination among federal statistical agencies. And he also is the Deputy Director of Information Initiative at Duke, which is an institute dedicated to research and applications in the analysis of large-scale and non-large-scale data. And then after Jerry's talk, we are going to have a discussant, which is Ed Mulrow, and he is the Vice President for NORC at the University of Chicago. Ed is an accredited professional statistician, and he is also a fellow of the American Statistical Association. He has over 30 years of statistical consulting experience, which includes sampling, utilizing administrative records, different Bayesian methods of evaluation, geographic information systems, visualizations, and data mining and record linkage. He's involved in several federal source surveys. He worked on the Medicare Current Beneficiary Survey. He worked on the National Children's Study with aspects of data linkage. And he's worked on the assessment of the Census Bureau's personal validation system and historical accounting of individual Indian money accounts projects for the Department of the Interior in their Office of Historical Trust Administration. Okay, so I'm going to cross our fingers that this is going to work right now in terms of WebEx. So we have Jerry's talk. So I'm going to hand it over to you now, Jerry.
All right, thank you very much. How's my volume? Okay.
Oh, looks like we need to increase the volume. So hang on one second.
Yep.
Coming up.
Turn the mic on, I think.
Okay.
Okay, go ahead.
Can you hear me now?
Is that okay for volume? Okay, everybody's nodding their heads, so go ahead.
All right, fantastic. Well, thank you all very much for the invitation to participate in the session. Thanks especially to Joe and Wendy. It's a pleasure to be having Ed as a discussant. I'm looking forward to hearing his thoughts. I should also note that part of my proud affiliation is that I'm a Schedule A employee of this Bureau as well. So I'm going to talk a bit about blending data through matching, modeling, and imputation. And this is an area that I've been increasingly moving into in my research. I think it's really fascinating and really important. And a lot of the ideas that I'm going to touch on are stem from work that's been supported by NSF through the two grants listed here, the first one being the NSF NCRN research network node that was here at Duke. Of course, any views expressed are those of me and not necessarily of NSF or the Census Bureau. So my goal here is to kind of give a broad outline of some general methods for blending data, for integrating data across multiple sources. I'm going to fly pretty high. I'm not going to get into technical issues, or really there's almost no math in this talk at all. Joe encouraged me to kind of speak in a way that hopefully would lead to conversation, and so that's what I'm hoping to be able to do. I'm going to talk specifically about statistical matching, also known as data fusion, and then imputation strategies when you have other data sources and you're trying to integrate them into an existing survey. I'm going to spend some time describing methods and then also talk about what I see as pros and cons of different methods and linking up to concerns about data quality and issues that agencies should consider when thinking about implementing or trying these techniques. I am not going to talk about record linkage. Becca's already done a great job there. I'm not going to talk about privacy concerns. Although that is not intended to minimize their importance, I think privacy issues are a huge part of all the blending, but there's just not enough time to get into that. Okay, stop me anytime with questions. So let's talk about statistical matching. And I think it's instructive to work with a real simple setting, just to lay down some ideas. We've got two files, a file A and a file B. And we have a file A that has some variables X and another set of variables Y. And these can be multivariate. If you want to make life easy, think of Y as univariate and X as a few variables, just to fix something in your mind. And file B has X as well and a Z. Okay, but file A and file B do not have overlapping sets of records. All the records are disjoint. So we have no simultaneous observations of Y and Z. But the whole goal is actually to blend file A and file B so that one can learn about the associations between Y and Z, possibly given elements in X, right? So this is the data fusion context. It's very popular in, for example, marketing, where you have a survey that assesses consumer behavior, how do you learn about books, and another survey that expresses or gets at consumer preferences. What are your favorite authors? And you'd really like to be able to combine the two of them, but you don't have anybody overlapping in the two surveys. How do you do it? So the fundamental problem here, of course, is that we can't estimate the joint distribution of Y and Z from the data alone because we don't have anybody with Y and Z measured. We have to make some form of identifying assumption. We need some form of external information in order to proceed here. And the way that this information is typically specified is generally through these three ideas. One is positing some specific assumption about the association between Y and Z given X, about that partial correlation, if you will. A very common assumption is that they're conditionally independent. Another is actually to try to go find another data set, which I'll call auxiliary data, which has Y and Z or pieces of Y and Z, and ideally X, observed simultaneously. But these are not the records that are in the files you want to integrate. These are in some other file or files, for that matter, and you want to use that information to help you with the integration. And then you may have constraints on the associations from other sources. You may not have individual record-level data, but perhaps you have summary tables that give you a sense of what the associations, what they might be, what's the strongest they could be, for example. Or I'm actually not going to talk much about the third bullet. I'm going to focus on the first two just in the interest of time, although I have been working in some of my research on thinking of ways that you can use known margins, say from a trusted source, and help you fix up non-ignorable missing data from unit non-response or item non-response by using those known margins. And that's another talk, which I'd love to give one day. Okay, so that's the setup. Let's talk about how people go about doing this statistical matching, and focusing first on assumptions about the association between Y and X. So the most common assumption is that conditional independence. That's pretty much what every application does. I haven't seen really any realistic applications that are not just people writing papers where they're not assuming conditional independence. And that might be just me being unaware of stuff. Please, I would love to be fixed of that misperception. But basically the idea is, you make some assumption that says, oh, I don't really need to know Z to learn about Y if I know X. Okay? And if you make that assumption, and it's an assumption of convenience really, because people think, well, what else are we going to do? right? If you make that assumption, you can do implement ideas like the following. So you can use something called for the nearest neighbor hot deck, right? So for each record in file B, say, we'll find the record in file A with the most similar value of X, or some subset of X, and we'll use its observed Y as an imputation for the missing Y for that record in file B. Right? So you're basically just going for file B records, you're finding somebody in file A who looks the same or similar on their X's, and then grabbing their Y. And you could do the same with file B, for file A, grabbing donors from file B. Okay? So that's the nearest neighbor hot deck type approach. Assumes a conditional independence because you're basically just grabbing values of Y based only on X. You're not grabbing them based on what the value of Z is. So that's implied in that method. And again, that is by far, the nearest neighbor hot deck is by far the most commonly used approach to the statistical matching, definitely in the as an industry standard. Regression modeling, so it's kind of related in a lot of ways to the hot deck, but you can, instead of sort of an implicit model, which a hot deck is, you can actually build a statistical model, a parametric model, say a regression, that predicts Y from X and use it to impute the missing values of Y in file B, and vice versa for file A, right? And that regression model could be whatever you want. It could be linear regression, logistic regression. It could be a machine learning technique. I mean, the whole goal here, in some sense, is prediction, rather than interpretation. And so that opens the door to all sorts of prediction engines that might be useful for this. Okay? So we could build those predictions, create this completed file B, basically, and file A if we want. Or you could build a joint model for all the data. And those could be any joint distribution. You basically can concatenate the data, if you will, append file B to file A, and posit some joint model for the data, a log linear model, a multivariate normal distribution, or what I've been working with in my research is thinking about really flexible, non-parametric, they have to be non-parametric Bayesian engines, but they're basically just models mixture models that try to allow flexibility in capturing relationships in the data that are not necessarily easy to capture with a standard multivariate normal or log linear model or thing like this. Okay, so those are three kind of ideas. The joint model is using a conditional independence too, because you basically don't have any information about Y and Z in the data, and that gets passed on through the joint model. So those are common methods that are used to implement statistical matching under conditional independence. Let's talk about some of the pros and cons. Pros. So let's talk about hot deck in particular. So it's very easy to explain, and I think that's why it's quite popular among the marketing industry. It's very familiar. Statistical agencies have a lot of experience with hot decks for imputation of item non-response, for example. It can generate realistic multivariate imputations. That's one of the motivations for people use hot decks, is so that they can try to grab existing cases and preserve that multivariate structure that's in the data. So those are some pros that I see for nearest neighbor hot deck. What are some cons? So the biggest one, of course, is the conditional independence assumption. It's a very, very strong assumption, and it's really hard to evaluate it. There's no information in the data to help you evaluate the assumption. And if it's not true, the matching very well could be unreliable. Right? And so what do agencies or people that use this nearest neighbor hot deck do in practice? Is they try to make X very rich, with the hope being that if you have two individuals that have the same X's on a lot of variables, that maybe knowing something about their Z doesn't tell you much more about their Y. Right? Again, a completely unverifiable assumption, but that's the name of the game in the statistical matching, where you've got to impose some assumptions. Okay? So that's one con. Another, of course, is the need to select the distance function and the subset of X that you want to match on. And like with any hot deck application, that can be tricky when you've got a high dimensional X with different types, ordinal, nominal, continuous. It can get a little tricky, or if you have multivariate Y and Z, you're trying to think of some metric to match on. You might want to use different X's for different Y's, different Z's, and what do you do there? So it can get a little tricky, and you can wind up sometimes having to do things like restrict the number of X's that you use in the nearest neighbor matching, sort of like in the type of hot deck restrictions that have to happen when you run out of cases, and so that sort of stuff can happen, and that can cause additional doubt about your assumption of conditional independence. The typical application that I've seen of this hot deck uses a single imputation. Grab the nearest X, take their Y, plug it in. Of course, that's a recipe for underestimation of uncertainty, because we plug in that Y into this file B, but that's not the real Y. It's got extra uncertainty attached to it, and I haven't seen really anybody dealing with that additional uncertainty. It's sort of ignored, and it matters here. It's not like you might make a case. Oh, well, if we have 5% missing data and we plug in single imputations, all right, we're underestimating uncertainty, but it's we're willing to live with that. But here, you're filling in an entire Y for every record in file B, so you have a high fraction of missing data in all likelihood. So that single imputation could really underestimate your uncertainty. Okay. And then it also can cause difficulties with edits. I mean, this is just a general issue with hot decks. It could be quite challenging to do edit imputation type routines to respect complicated edit rules when you're doing hot decks. And particularly if you think you're doing a nearest neighbor and maybe they're on the X's they match, but then you plug in the Y and somehow an edit violation happens, and it can just get a little bit complicated and messy to deal with. So those are what I see as some pros and cons of the hot deck. What about some quality concerns? Okay. So there are a lot of ones that are going to be the case for any kind of data blending exercise, right? So clearly we have to make sure the X variables are defined similarly, right? If you're blending two databases and you're matching on a variable that the questions are asked slightly differently, your matching might be thrown off, right? So that's really important to make sure it's harmonizing the X variables before you do this exercise. Are the data files contemporaneous? Are they, in some sense, are they representing the same target populations? Right. These are important questions, and it can get that can become problematic, particularly when you're blending, because very often we're thinking about using some file that was collected months or even years ago, and so have relationships changed in the intervening period, and if so, that could throw us off. Complex designs can be tricky to deal with here. So, for example, if you want to concatenate the two files, okay, and release or analyze this concatenated file, and if the files are from complex designs and maybe different designs, and they have weights, and you've got to somehow reweight the data so that the concatenated file represents some target population. And it gets kind of tricky, in my mind, to think about, particularly if your surveys were collected with quite different designs. What exactly, how do you do a design-based difference if that's what you want to do in that context? There is some work on this reweighting, and I know agencies are very good at it. There's a paper by Rubin, and I think it's 1984, where he talks about data fusion and reweighting. And I should say, by the way, that I haven't listed any references, but I'm happy to send those along to Joe and Wendy after, if that's of interest. Okay, so anyway, you could imagine concatenating the data and then figuring about the weights is tricky. Or you could actually think about using only one file for analysis. right? So maybe you just use file B because that's the more current file, say, and so putting together file B and file A creates a kind of a strange target. It doesn't even really think about a strange target. What target population does it represent? I can't even think about that. So I'll just analyze file B, but I want to use file A to help me do those imputations of this missing Y. Right? So that might be a way to go, and then you have the design and the weights from file B, and you don't necessarily have to mess with that, which is good. That does create some intriguing issues in terms of accounting for uncertainty. So, one of the approaches that you can imagine doing here, not necessarily with a single imputation hot deck, but some sort of multiple imputation, or I saw Stas is chatting with fractional imputation, but some sort of way of propagating uncertainty. Well, it's going to turn out that if you do sort of one file, you release one file, but you use another file to fit the models, that the standard multiple imputation combining rules of Rubin 1987 don't work. You've got to, they don't give you valid variance estimates, and so there are other rules that have been developed that can give you valid variance estimates, but you do have to be careful here. Oh, and that leads to the next bullet. So propagating the uncertainty, right? And again, I think about creating multiple data sets to propagate the uncertainty, and particularly, there could be multiple hot decks that you might want to do in some sense. So not only once you fix a matching algorithm or fix a conditional independence assumption, right, you might want to create multiple data sets there to see what kind of uncertainty there is. But there's also potential for doing sensitivity analysis where you might want to, okay, well, I want to see if this conditional independence assumption is kind of really driving all my results. How sensitive are my ultimate analyses to other kinds of assumptions about the relationship between Y and Z given X? And so having multiple copies of the data, either for analysis or dissemination, can be quite useful, I think. And actually, those sensitivity analyses, they can be a little bit tricky with the hot decks. I guess you've got to think about alternative matching algorithms or alternative distances, and to think about sensitivity. Again, that to me is a little unnatural, but that's just my opinion there. Okay, so what about other approaches? So, okay, well, we could still be in that world of conditional independence and think about statistical matching as a regression problem, right? So you could do a regression of Y on X and use that regression to impute the missing Z's in file B, and vice versa in file A if you want for Z. Okay? You also could expand that idea a little bit and think about the regression approach as something like this, right? Just to write down, let's say, a model for Y, which would be some function of X beta plus a Z times an alpha. Plus an error term. Just think of a normal linear regression if you want, but I'm intending to be generic here. Okay? A conditional independence basically sets the alpha to equal to 0. Okay? But again, there's no information in the data that says alpha should be 0. You're just sort of you're just assuming that. Okay? You can set alpha to something else. Right? If you wanted to perform sensitivity analysis, you could say, well, why don't I put alpha corresponding to a value that has a partial correlation of 0.5 or 0.8 or other things like this, right? Then you could essentially, once you fix that alpha, you could still estimate the betas if you want. Just plug that alpha in. And then you could generate these imputed Ys under multiple plausible models and assess your downstream analyses. Right? In one sense, the sensitivity analysis a little weird in that, okay, well, if you fit a model for Y on X beta plus Z, you'd get exactly back what you put in. Okay, so there's nothing there. But on the other hand, you might want to use the completed data sets for some other analysis. Maybe you want to look at a subdomain mean for two groups, compare two subdomain means, and that may not be quite as obvious what the difference, how sensitive those results would be from whatever imputation model you put in. But once you make a data set, it'll be really clear that you can assess the sensitivity of those analyses. So I like this idea of doing sensitivity analyses around statistical matching. I don't see that done very much, to be honest with you. Most everybody assumes conditional independence and goes. But I really think this is a valuable way to think about this blending. Pros and cons and quality concerns of using regression modeling approaches. Well, I personally find these regression models potentially to be more flexible than the hot deck approaches. So, and particularly nowadays, where we have all these amazing advances coming out of machine learning for doing this, getting these predictive engines, and so we might be able to leverage those to come up with really good prediction models, for Y given X. There's an interesting research question there about how you can incorporate sensitivity analyses. If you're doing that, you can imagine ways that you might be able to do that kind of ad hoc. But let's increase Y by 20%, or predicted Y by 20%, that sort of thing. But actually thinking of principal ways to do that is an interesting area for research that I haven't seen much on. There's regression models out there that satisfy edits. Nice paper by Shlomo and I forget I think it was Tandewal, I think, that talks about that. I have some work in that space too. You can sort of check the quality of the regression model, which is nice. I mean, it's just a standard regression modeling exercise of Y on X, so you can work hard to get a good model for Y on X and use all the existing diagnostic techniques that are out there. That doesn't help you check the conditional independence assumption or whatever alpha you decide to put in there, but at least you could feel somewhat more comfortable about the quality of your Y given X model through standard diagnostic ideas. Again, I see it as a prescriptive and flexible approach to sensitivity analysis. You can plug in parameters, and then it sort of naturally leads to multiple imputation for uncertainty propagation. Well, the cons, again, you cannot escape in the statistical matching data fusion world. We cannot escape the need to make unverifiable assumptions about alpha. There's just nothing we can do there. And, of course, we have to select a model, and that always entails some risk of misspecification. But that's always the case. Even with a matching algorithm, there's a risk of misspecification there. And all the same quality concerns about contemporaneous data and harmonizing X's, and et cetera, apply here as well. Okay, let me switch gears a little bit. My last 15 minutes or so is if we have auxiliary data with Y and Z observed, right? So there's statistical matching, and you have to impose assumptions in order to identify that joint distribution. Another way you might be able to identify it, or at least partially identify it, is if you have other data sources where you do have Y and Z observed simultaneously along with X. You may not have all of Y and Z, you may not have all of X, but you have at least some of them. And you'd like to use that information to help reduce the reliance on conditional independence assumptions when you're doing this sort of imputation or model-based approach to these fused data sets. So let me just sort of lay out three cases where the first being sort of all variables in Y and Z are observed for all variables in X. Obviously, that's the pipe dream, but it's really more for getting ideas down. The more likely cases are the second and third, where we start to think about pulling together information from different sources and patching it in to come up with some estimate of this joint distribution of Y and Z and X, or Y and Z given X. Okay, so let's do the first case just to fix some ideas. So really it's quite simple, right? So we're going to regress Y on X and Z and use the model to impute the missing Y in file B, and likewise for Z in file A. And you could do a multiple imputation here to propagate uncertainty if you would like, okay? Which I recommend. So, of course, the overarching quality concern here is essentially the conditional distribution that you fit in the auxiliary data must be valid, must be reasonable for the conditional distribution for the records that are in file B. Okay, and that has you could view that overarching quality concern in lots of ways. Again, similar time periods, similar target populations, similar sampling designs. You might be able to account for differences if possible using, say, some survey-weighted modeling techniques or related approaches. But in general, you want these distributions to be reasonably similar, and of course we've got to specify a good fitting model in the auxiliary data. All these concerns are going to hold for the second and third cases, which are much more complicated. Right? So let's talk about that second case. So we have one auxiliary file, which basically has some of the variables in Y and Z observed jointly, observed simultaneously, and possibly some of the variables in X. It may not have any variables in X, maybe just Y and Z. But obviously we need some variables in Y and Z observed, or else this doesn't really help us that much. Okay? So, this is a hard problem, and this is the research part that I'm getting really interested in. So one of the one approach here that kind of makes it easier is to specify a convenient multivariate distribution, right? So, and then for some multivariate distributions, you can kind of have parameters that correspond to these marginal distributions that you can estimate from the auxiliary data, and you can basically estimate those distributions and plug in the relevant parameters. So the classic example would be like a multivariate normal distribution, right? So the key thing there, of course, is the covariance matrix in that distribution. You need all the covariance terms. You have all the variance terms, and you have all the means from the data you have, the survey you have. But you need the covariance terms. So you can get those, for example, by saying, I look at my auxiliary data, I have the covariance between Y and Z. Great, I might be able to bang that through, right? To plug that into the multivariate normal distribution between Y, X, and Z, and then I've partially identified my model. I haven't fully identified it. There are still parameters in there that the data won't support, but I'll probably have constrained what those parameter values could be by adding in more information. More generally, if you don't want to have to lean on a multivariate normal or log linear model or something that has convenient, sufficient statistics, if you want to have something flexible because you've got mixed type data, if you have some arbitrary joint distribution. So here's kind of an idea, and this is what one of the ideas that my group has been playing with. And so what you can do is take your auxiliary data that you've got, append it to the bottom of the file B that you have, right, the survey file. This is just a file B and an auxiliary data. That's kind of what I'm thinking here. And estimate that joint model using this incomplete data set that you've created, right? So you have basically some of Y and Z observed and some of X observed for these appended observations, and you have some Y's observed, Y and X observed, or Z and X observed, sorry, for file B. You create this big concatenated data set and try to treat it as a missing data problem, right? So you can fit a joint model to that. It could be a flexible joint model, a mixture model. It could be a multivariate normal, whatever you want, and that will essentially create completions of the missing value as part of the fitting process, right? You got to be a little careful in how you do this, though. So one of the things that we've learned is you might have to construct the appended data. So the appended data might give you a conditional distribution of Y given Z, or some elements of Y given some elements of Z and some elements of X. Okay, but you don't want to just add all of those X, Y, Z's jointly as data. You actually need to respect the marginal distributions of X and Y and X and Z that were in your original survey, your file B that you're doing. If you just add sort of non-representative data, for example, to the bottom of a file and then estimate a joint distribution, it will mess you up. The estimates will be wrong. I don't get into the details there, but I'll point you to a paper that we wrote in Annals of Applied Statistics where we did a data fusion problem of two marketing surveys, one on consumer preferences and one on consumer behavior. And we actually got an auxiliary data set using a rapid response online polling company, and I'll talk a little bit more about the application in a second. But that gave us pieces of Y and Z. What authors do you like, and how do you find out about books? Those were Y and Z, and X's were things like age and income and sex, etc. And so we got pieces of those. We didn't get the full thing, but it turned out that the joint distribution of the data we got from the company Civic Science was clearly not representative, but maybe the conditional distributions were. So anyway, there's an example of how you could create this appended data so that you don't run into that problem in the paper here. Okay, what about the third case? So now you've got multiple auxiliary files, and this is kind of, I think, the direction that we're all interested in going. You have all these files all over the place, and you get partial information about all sorts of variables, and really what you like to do is create this gigantic joint distribution of all the data that you have, right? That would be super cool. Again, for specific joint models like the multivariate normal, you can estimate your various covariances from all the data you have, plug them in, and have kind of a partially identified model. But if you want some arbitrary joint distributions, I haven't seen a lot of work in this space. I mean, conceptually, one could use this idea of stacking all the data sets but adjusting them to make sure you have the marginal distributions of the variables that you have in the original file aren't distorted when you stack all the data sets. To my knowledge, no one's really tried that yet. We've been playing with it in simulations, but I don't think anybody's tried it in real data. That may not be. I might be wrong on that. I would love to be wrong on that and hear some feedback from the audience. Pros and cons and quality concerns of this whole idea. So pros. So well, the use of auxiliary information, so it can reduce the reliance on unverifiable assumptions, which is great. We can specify models that satisfy edit constraints, and we have a way to check quality of auxiliary data models for predicting the marginal distributions in the observed variables. So that's kind of a partial check on the sensibility of the models. It's not a complete check because we still may not have all the joint distributions to observe, but at least for ones we have observed, we can do a check. And of course, it leads to multiple imputation. Cons, we still have to choose a model and make some unverifiable assumptions about the marginals and conditionals that are not observed. We have to think carefully about constructing this auxiliary data, and if we want to use flexible models, it could be a little tricky to think about sensitivity analysis. Okay, so let me have a couple more slides. Thoughts on what agencies might report in this blending. So I think if agencies are performing statistical matching, they should be transparent, definitely about all the metadata for the files. The users need to be able to decide if the variables are asked in similar ways and those sorts of things, and get the study designs from the different files, et cetera. All that, of course. Any steps taken to harmonize X variables, any edits that were made, all those things, because we're going to be doing a lot of imputation in this context. Right? And so we really want to know everything. All the assumptions in the models used in the matching, the matching method, the X's that were used in matching, et cetera. Assessments, if you're doing regression modeling, assessments of the quality of the fits, give people a little faith that at least these regression models are decent. And then I personally am a big fan of sensitivity analysis, and I think it's important to do that if you're releasing results, or release multiple data sets if you're putting them in an RDC, FSRDC, or something or the like. In addition, if you're using auxiliary data, I would suggest being transparent about potential selection biases in the auxiliary data. I'm thinking here of the civic science example. In our data set that we got from them, there were far more older people that responded to the online poll of civic science than there were in the original survey. And that sort of information, I think, should be made available to the users of any fused data constructed with that. All the conditional distributions that were used. The third one's a little bit harder, but I think it's important to find a way to release information that what variables were not jointly observed, so that users know that associations based on those variables that were not jointly observed, they're going to be a little dicier. Thoughts on research directions. This is my last slide. So I actually really think this idea of getting really convenient, even though it's non-representative auxiliary data, is intriguing, right? And in some ways, with all the organic data and administrative data, we're kind of getting to that space as it is. So in our paper, we we had Civic Science who did this for free for us. They were really nice. They basically did a quick poll. You know, they post these internet polls on the where people go to like the Dallas Morning News and they answer 4 questions. And so you get hundreds of thousands of responses in an hour for very low cost. Okay, I would never use that to make to learn about joint distributions because it's so obviously biased. But maybe you could learn about conditional distributions, right? Maybe those are okay, and you can kind of check that by looking at the conditional distributions, say of y given x in your convenience sample. Compare that to the distribution of y given x in your original data. If that's close, at least it's some partial hope that it might be okay. All right, so how can we use these sorts of convenience samples effectively to start learning about pieces of that YZ joint distribution that we don't have? I like this other approach, the last approach I mentioned of sort of trying to pull together all these conditional distributions from all over the place and see if we can't, come up with the big data set, imputed, of course, that tries to capture a lot of relationships. How do we actually go about doing that? That's a hard problem, just practically, as well as statistically. And then if you're doing that, how do we give these quality measures? How do we, in a coherent way? I mean, you can imagine just this gigantic list of what's been observed together and what's not. But that just reminds me of a gigantic edit constraint list, which nobody really understands, right? And so it'd be nice to kind of figure out ways to do that. That's a communication exercise, I think. I also think that thinking about how you can propagate uncertainty in this context is important. The initial simulation studies suggest that existing multiplication combining rules aren't quite right. So that's basically my talk. So do you need me to not share, to get off the sharing?
Yeah, can you stop sharing just in case? I think I can boot